so now this is unit 7.2. It's actually going to be a 2-day lesson. So part 7.2 is going to be the fundamental theorem of calculus part A. We're going to talk about 2 different parts of this today, and then next class we'll talk about the second half of our fundamental theorem of calculus. So the very first one we're going to talk about is called our integral evaluation theorem. And this is something you guys have already kind of seen. When we did our review, we talked about it. We did n minus beginning. So that's really all we're going to talk about today, is this whole concept that if my f is continuous at every point, yada, 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 then this is only saying that if big F is my integral, as we remember, so this is saying that I'm going to evaluate my integral at B minus my integral at A. We did that, but we're going to actually do some example problems today. So very simply, let's just start with a very easy evaluation. We're going to do the definite integral from -1 to 3 of x cubed plus 1. So let's first off, step 1, when I'm doing my fundamental theorem of calculus, or whenever we're applying a definite integral, is step 1 is we have to figure out what is our integral. We need to know that. So let's figure out the integral. So simply put, we're going to do the integral of x cubed plus 1. I suppose I should have left myself a little room. Okay. Now we're going to apply our power rule. It's the only rule we've learned at this point. So we're going to apply our power rule, and we're going to do plus 1, second step, all over my new exponent. But what do I do about this x? Well, this is a property of integration, just like with our derivatives. Whenever we saw 7x or 10x or whatever, we knew that the derivative was just going to equal our constant value. We just knocked off that x. Well, what happens when I integrate at a constant value? I'm just going to tack on my variable. But if I wanted to prove that, let's just assume this is x to the 0th. What's anything to the 0th power? It's just 1. So if I apply my rule, so plus 1 over 0 plus 1, well, this 1 on bottom is not going to affect us. And then anything to the first power is simply itself. So this tells me that this now becomes 1x or x, and that's just a property. In the future, I don't expect you to apply it like this. Like you don't have to do all of this. I know that anytime you see the integral of some constant number, you are going to know that that's immediately 7x, or the constant when tacked onto my variable. Okay. So then if I tally this up, this becomes x to the 4th over 4 plus x. And it's a definite integral, so I don't need to tack on plus c because we're actually going to evaluate it at those points. So I'm going to just draw my evaluation from -1 to 3. And so what that just means is that I'm going to evaluate this little new function, my integrated function, at 3 and at -1. Well, how do I know which order? We go from A to B, but we subtract B minus A. Remember, our formula was f of B minus f of A. So in our instance, we're doing f of 3 minus f of -1. So let's evaluate that. So if I have my f of 3, we're going to do 3 to the 4th over 4 plus 3 minus my f of -1, which is -1 to the 4th over 4 plus -1. So if I go ahead and solve that, if I continue my solves, 3 to the 4th is 81. 81 over, is it? No. 27, yeah, 81. 81 over 4 is, man, I'm suffering at math right now. 32? Okay, so 81, so this becomes 81, and this becomes 81 over 4 plus, and we don't want to have 3 as a whole number, we want to have it as a fraction, so this becomes 12 over 4 minus negative 1 to the 4th power. 4 is an even number, so my negative 1 is going to become positive 1. So this is 1/4 minus 1, so minus 4/4. This becomes 93 over 4 minus, this is negative 3/4, so plus 3/4. So this becomes 96 over 4, which is just 24. And that's my end answer. And I realize it seems like we did so much work just to get to one small answer, but that's all we're doing is we're evaluating from f of b minus f of a. So most of this work is actually algebra. It's not even calculus. This was the only calculus we did. Okay, so this really shouldn't be a scary concept today. It's just a little bit of work. And if I want to double check that answer, it is 24, so we did a correct job. We did it correctly. But let's explore something a little further. Let's look at this 4 minus x squared. Well, what is that parent function? It's a parabola, it's quadratic. And in fact, it's a downward facing parabola, it's a downward facing quadratic with a transformation because of that 4. And so what is it asking us to find? It's asking us to find the area of the region bounded by our curve and our x-axis. And we've done that before, haven't we? That's just our definite integral. So I went ahead and got a graph for us. And we can actually see from 0 to 2 is going to be our positive area, from 2 to 3 is going to be our negative. And I went ahead and calculated those values for you. So from 0 to 2, it's actually 16 over 3. From 2 to 3, it's actually negative 7 over 3. As we remember previously with our definite integrals, our area under the curve, all we do from 0 to 3 is add up these areas to get a net area. So if I add up 16 over 3 and negative 7 over 3, I should get 9 over 3, which is simply 3. My answer of 3. Well, why did we do all of this work? Why are we going backwards talking about old concepts? Okay, so our new concept today is the fundamental theorem of calculus. Why don't we try applying our fundamental theorem of calculus here? So my integral of 4 minus x squared, I should be able to figure that out pretty easily. The integral of 4, I just tack on my variable, so this becomes 4x. The integral of x squared, this becomes plus 1 over 2 plus 1, so that becomes x cubed over 3. So I'm going to evaluate 4x minus x cubed over 3 from 0 to 3. Well, first things first, what are my f's? So f of 3 minus f of 0, because we're going from n to start. Let's talk about f of 0 for a second. Or do I have x's throughout? If I plug in zeros in those x's, is my whole value going to become 0? Yes, it is. So I don't need to deal with that. All we have to worry about is f of 3 in this instance. So let's plug in our 3. 4 times 3 minus 3 cubed over 3. This becomes 12 minus 27 over 3. This becomes 9. 12 minus 9 is 3. Are those the same answers? Absolutely. So what does this show you? Is there a relationship between the fundamental theorem of calculus and my area under the curve? Absolutely. This is where they come from. So let's actually work on some of our example problems before we get to our second set. So we're going to evaluate the definite integral from negative 1 to 3 of 4x minus 2. Well, step 1, I need to figure out my actual integral. So my integral of 4x minus 2 is going to become 4x minus 2. This is going to become squared over 2. This is going to become x. I can simplify, and I'm left with 2x squared minus 2x. Well, we want to evaluate 2x squared minus 2x from negative 1 to positive 3. And again, we ask, what's our b and what's our a? So our b is our end point, our a is our initial point. So this is going to become f of 3 minus f of negative 1. And from here, all it is algebra, it's arithmetic. And I'm going to just plug in my values. So let's plug that in. Let's say this is 2 times 3 squared minus 2 times 3, all minus 2 times negative 1 squared minus 2 times negative 1. And then we just evaluate from there with some math. So 3 squared is 9, 9 and 2 is 18. minus 6, so this is actually 12 minus, so negative 1 squared is just going to be positive 1, so this is just 2, and then negative 2 and negative 1 makes you positive 2, so this is actually 4. 12 minus 4 is just 8. Is that my correct answer? It absolutely is. So we did all this work. Again, as I said, this is the only calculus over here. All of this is just plugging, chugging. That's all it is. So, I went a little far. You guys got a preview of the answer, but that's okay. We're going to solve it and verify if our answer was correct. So first things first, I need to find my integral. But in this instance, with my integral, I have to do a tiny bit of algebra manipulation. So I'm going to say this is actually now going to be the definite integral, and we're going to do 1/2 times x to the negative 2 dx. Well, now I can actually evaluate that a little bit easier. So again, we add 1 up here, we divide by our new exponent. So this just becomes 1/2 times x to the negative 1 over negative 1. The 1 on bottom doesn't matter, but my negative does. So this becomes negative 1. I just told you it matters. Negative 1 over 2x. Well, how did my x come to the bottom? I got rid of that negative exponent. This is going to be a prime example of why we get rid of negative exponents and why we get rid of fraction exponents. Because of today, we do that FTC when we evaluate our values, our a's and our b's. It's easier to see 1 over 2x than it would be to see x to the negative 1. In the end, you can do it however you want. It's math multiple ways. So we're going to evaluate it from 1/2 to positive 1. And so we're going to say that's f of 1 minus f of 1/2. And let's go ahead and evaluate those. So if I say this is negative 1 over 2 times 1 minus negative 1 over 2 times 1/2. Okay, well my 2 and 1/2, that's going to cancel out. My 1 down here is going to get rid of it, doesn't matter. So this becomes negative 1/2 minus positive, minus and minus, so it's going to become plus 1, which we want to do in the form of 2 over 2, which just equals a positive 1/2. And that is the answer we saw very briefly at the beginning of this slide. And I'll show it to you again right here. We did get that answer, so we did a correct job. Excuse me, sorry. So let's look at example number 5. Again, a tiny bit of algebra manipulation because we're going to change the square root of x to the 1/2. But if I look at that integral, then we know that that's going to be x cubed over 3, because x squared is going to be 2 plus 1 over 2 plus 1, so x cubed over 3, plus, I got to do a tiny bit of that, so x, that will be 3/2 over 3/2, so this is going to become 2. Okay, so this is going to become 2 square root of x cubed over 3. And I'm going to evaluate that from 0 to 1. And so we're just going to apply our fundamental theorem of calculus. So f of 1 minus f of 0. Well, I have a 0 value. Let's check if it's going to affect us today. So if I plug in 0, 0 here is going to cancel this, 0 here is going to cancel this whole value. So do I even need to evaluate my f of 0? I do not. That makes our life a little bit easier. We're just going to evaluate f of 1. So this becomes 1 cubed over 3 plus 2 times the square root of 1 cubed over 3. Well, 1 cubed is just 1, so this just becomes 1/3. 1 cubed is still 1, the square root of 1 is still 1, so this just becomes plus 2/3, which is just 3 over 3, which is just 1. If I want to double check my answer, it tells me my answer is 1. We did it correct. Good job. All right, let's look at a released AP question, because these kinds of questions are rampant throughout the non-calculator portion of the exam. So very simply put, we want to figure out first things first, what is our integral? So our integral of 4x cubed, we're going to add 1 and divide by the new exponent. So it becomes x to the 4th over 4. My 4's are going to cancel, so this just becomes x to the 4th minus 6x will become 6x squared over 2, so it's just 3x squared. And we're going to evaluate that from 1 to 2. So here we have to look at f of 2 minus f of 1, and we're going to go ahead and plug that in, just do our basic math. So this becomes 2 to the 4th minus 3 times 2 squared minus 1 to the 4th minus 3 times 1 squared. And if I do some of my math, it becomes, what is this? 8, 16, 4, and 12. So this actually becomes 4. And this is 1 minus 3. So negative 2. So minus and negative 2 becomes plus 2. And my end answer becomes 6. And if I double check to make sure I didn't mess up on my math or somewhere in between, my answer was 6. Very good. All right, let's look at example number 7. Here we have to do some algebraic manipulation first, so I'm going to go ahead and begin with that. So we're actually going to be looking at the definite integral from 0 to 4 of 1 minus x to the 1/2 times x to the negative 1/2. So if I bring these across, this just becomes the definite integral from 0 to 4 of x to the negative 1/2 minus, these are going to cancel out, so minus 1. And then now I can actually apply my integral, my power rule, so this becomes plus 2 over 2 over negative 1/2 plus 2 over 2. And this one I just tack on an x. So this becomes positive 1/2, positive 1/2. So this is the same as saying positive 1/2, I'm going to flip it. So this is going to be 2 x to the 1/2 plus x. But again, we don't want to see this as x to the 1/2. We want to get rid of that exponent as a fraction. So it becomes 2 square roots of x plus x. And we evaluate that from 0 to 4. So again, we're going to plug that in. This becomes f of 4 minus f of 0. First things first, I have a 0. So is that going to affect our answer? 0, 0 becomes 0, so I don't need it. So let's go ahead and evaluate our f of 4. So that becomes 2 times the square root of 4 plus 4. 2 square roots of 4 is 2 times 2 plus 4 gives me 4 plus 4, which is just 8. I double check my work, make sure I did it. Oh no, where did I mess up? Oh, I see it. And this is why we check our work, people. I'm gonna make that smaller because my mistake is all the way back here. This was minus, and somehow I put a plus. Who knows why? So this should have stayed minus. So my new answer should have been 2 square roots of 4 minus 4. So that becomes 2 times 2 minus 4, which is 4 minus 4, which is 0. Okay, it's always smart to check our work. Very good. And now we're actually going to look at, we're going to kind of go backwards for a second and just go back to our area under the curve. Just do a little preview, just do a little review of that. So if we went from 1 to 1, have we moved anywhere? No, so my answer should just be 0. That's a property of integration. So if we know that the definite integral from 1 to 1 of f of t dt would just be equal to 1. That was pretty easy. What about from 1 to 3? Well, did we move? Yes. Did we create a shape? Absolutely. In fact, we created this triangle right here. So I know this triangle is going to be 2 even little right triangles, so I can see it as one giant one. So it's a base of 2, a height of 1. So 2 times 1 is 2. 2 over 2 just gives me 1. So this area right here is positive 1, but are we sure it's positive 1? Not quite. It's under the x-axis, so it's actually negative 1. What about from 1 to negative 1? Well, what shape did we create? Well, this whole shape right here is a semicircle, so half of that means it's a half of a semicircle or a quarter of an original circle. So if we look at that, what's the area of a circle? Area of a circle is pi r squared. We're taking a quarter, so it's going to be over 4. It's as simple as that. What's our radius? Well, this is my halfway point, so 1, 2. So this becomes 4 pi over 4, which just is pi. But am I done? Not quite, because we're actually going backwards, aren't we? From 1 to negative 1 takes me negatively on the x-axis or on the number line. And so this isn't just going to be pi, it's going to be negative pi. So I know that my definite integral from 1 to negative 1 of f of t dt is going to equal negative pi. That's my answer right there. What about if we look at till negative 3? So from 1 to negative 3, we're actually doing the whole semicircle. And so if our quarter of a circle was pi, what's our semicircle? 2 pi. Are we going backwards? Yes. So my definite integral from 1 to negative 3 of f of t dt would just be equal to negative 2 pi. And finally, we're going from 1 to 4. We know this distance right here, this area is negative 1. Well, if we look at this triangle right here, this has an area of 1/2 because I have a base of 1, height of 1. This is a positive 1/2, so negative 1 plus positive 1/2 gives me an area of negative 1/2. So my integral from 1 to 4 of f of t dt is going to be equal to negative 1/2. Continuing on, let's actually look at another AP style question. Our example 9 is where we're solving for k. And we've seen this before last semester when we talked about like continuity and solving for k and stuff like that. We're going to do something simple, something different, something similar, except we're going to use integration. Well, how do we do this? First things first, is this a definite integral? Absolutely. So can I apply my fundamental theorem of calculus? Absolutely. So step 1, do I have to figure out my integral? Yes, I do. What's the integral of x to the 7? 7 plus 1 is 8, all over 8, so it's going to be x to the 8th over 8. But what's the integral of k? K is some constant value, so what's the integral of any constant value? Well, it's the constant value, and I tack on my variable. So my integral is actually going to be equal to x to the 8th over 8th plus k of x, or kx, sorry, k times x. And we're going to evaluate it from negative 2 to 2. So all we do at that point is do f of 2 minus f of negative 2, and we plug and chug. So if I plug that in, that becomes 2 to the 8th, 256 over 8, I think is 32, plus 2k, and then again, negative 2 to the 8th, it's an even number, so it's still going to be the exact same value, minus 2k. If I distribute this, then my 32's cancel out, but my 2's actually combine, and I get positive 4k equals 16, and from there it's just some math manipulation, and we get 4. It's as simple as that. The hardest part about these questions is not the math itself, it's understanding the question and being able to start your setup. Same with this question. Example 2 is another released AP question, example 10 is another released AP question, but this question, it's just weird to read. It's not a hard question, it's just weird to read. The very first weird thing comes from the first few words. If little f is the antiderivative, well, that's crazy. Up until this point, big F has been our antiderivative. This is how they like to trick you. They like to say that little f is now the antiderivative because they know you're so used to seeing big F. Well, if little f is my antiderivative, and I know that I'm going from f of 1 to f of 4, does that look like my fundamental theorem of calculus? It sure does. So if it's my fundamental theorem of calculus, can't I just say that what they're asking, all that nonsense, all that hula, is going to just be from 1 to 4 of x over 1 plus x to the 5th dx. And in this instance, we actually were given a calculator, so the calculator allowed a portion of the test, and so you were able to just, if you could figure out your setup, that's supposed to say 4, by the way. Okay? If you could figure out your setup, you would have been able to plug this into a calculator, get your answer, and move on. Oh, I lied. There's actually one more step. Let me get rid of that. Okay. So once you plug into the calculator, you get this 0.248. But I lied. Can't move on. We're not quite done. Because this is the answer of this definite integral, but that's not actually what they're asking you for. In fact, they're actually asking you for f of 4. So we know that our fundamental theorem of calculus tells me that the definite integral has to be equal to the evaluation of my integral of 4 minus my integral of 1. Well, do we have this information? Do we have anything here to fill in? We sure do. We know f of 1. We know f of 1 is actually equal to 4, so from here it's simple math. To get rid of this 4, I add 4 to my other side, and my answer just becomes 4.248 or 4.249. Now, can I tell you, I guarantee that there would have been, if this is multiple choice, there would have been distracting answers. There would have been this answer, and Miss Jag maybe would have gotten caught because she tried to stop right there. But there would have been this answer. There probably also would have been, if you had accidentally manipulated the wrong way, instead of adding 4, subtracting 4, that answer probably would have been there. So those distracting answers are there. Like I said, not a very hard question to set up. It's simply, they're going to try and distract you. They're going to try and confuse you by changing big F to little f. They're going to try and confuse you because you might solve here and think you're done. They're going to try and confuse you because what if you set this up in the wrong direction? What if you do f of a minus f of b, etc., etc. There we go. Okay. Example 11 is another AP release question. So here we're looking at variable manipulation. So saying that if my definite integral from a to b is equal to a plus 2b, well, let's just look at that left half first. We're not even going to look at the right half first. What is this saying? A plus 2b? Well, isn't that just saying my fundamental theorem of calculus is going to be equivalent to a plus 2b? So I know that I'm done there on the left side. All right, well, look at this right side. Well, isn't this a sum and difference? Can I pull that apart? Absolutely. So let's go ahead and pull that apart. So if I pull it apart, I can see here's my first one, and I know that that's equal to a plus 2b. And here's my second one. Well, this is pretty simple. If I want to manipulate this, this would be the same as saying the definite integral of 5x from a to b. So it's the same as saying 5 times b minus a, because that's just going to be f of b minus f of a. And if it's just x, then that just has to be b minus a, right? So if I plug that in, that becomes a plus 2b plus 5 times b minus a. Again, this is just my fundamental theorem of calculus. If I keep going, I just continue on, and I see that's it. That's my end answer. I have no other way of solving for a or b. They didn't give me any more information. If this were a multiple choice question, your hint would be, because you would see similar answers in your four answer choices, so you would know that you're just doing variable manipulation. Now let's talk about part 2 of today's lesson. Let's talk about our average value theorem, which is our mean value theorem for definite integrals. So this is saying if f is continuous at every point, then my average value is going to be equal to this ratio, this fraction right here of 1 over b minus a times my original definite integral. So this part hasn't changed. This isn't new information. This is old information. The only thing we're adding on when we see the words average value in a question, this is all we have to tack on. Of course, we still have to manipulate this, we still have to solve this, but this is the only change we're making. So let's solve a question like that. Let's look at, again, they tell us average value. That should clue us in. We're going to do 1 over b minus a. And first thing first, we're going to evaluate 1 plus x squared of our definite integral from -1 to 2. So let's set up that original. Here's that formula for average value, just kind of a reminder. And so there's our setup. Here's our 1 over b minus a. Our interval gave us a and b. From -1 to 2 of 1 plus x squared. If I continue that evaluation, which this part, this half, you should be able to do at this point. So if I continue that evaluation, this would give me, in the end, it would give me 6/3, which just gives me 2. So again, like I said, the only real difference is simply adding this 1/3 in this instance, or 1 over b minus a to the front. Okay? So let's look at this example 13. This is a calculator allowed question. It was a released question. step one, step one, like what are we doing? Okay, average value. So we know we're using our definite integral and just tacking on at the beginning 1 over b minus a. So we know our a and our b, and we know our our y equals, but this is a calculator allowed question. So at this point, I don't know how to integrate that, or we don't know how to integrate that, right? Because at this point, we've only talked about the power rule. So let's go ahead and set this question up so that we can enter it into our calculator and check, did we get the right answer? So we have the definite integral from 0 to 2 of x squared times the square root of x cubed plus 1 dx. But again, this is average value. So what do I want to tack on to the front? I want to tack on 1 over b minus a, which is 2 minus 0, so it's just going to be 1/2. So if I plug this into a calculator, which I have, let's get rid of that. Let's go to our calculator. I manipulate using my math buttons. And I'm going to look at my definite integral. We said from 0 to 2 of x squared times the square root sorry, put my square root in the wrong spot. Let's try that again. Okay, there we go. Square root of x cubed plus 1. Our variable is x, so with respect to x. And my answer was 5.778, but again, I'm not done. I didn't actually enter in the initial value in the front, that average value addition, which is 1 over b minus a. In our instance, that was just 1/2. And so my actual answer became 2.888. And if I double check that, then my answer is correct, 2.888. So again, if this were a multiple choice question, I guarantee you that 5.77 or whatever, just the definite value answer would have been one of your answers, and so that would have been a distracting answer. If you forgot to incorporate this average value portion of it, that you would have gotten the incorrect answer because that answer would have been there.